Welcome back to College Algebra. Today we're going to be looking at section 2.4 on complex numbers. Just a quick reminder as you begin working through this section to look at the blank notes, to attempt some of those try-it problems on your own, then to look at the completed notes and see if you can get some help from it, and then watch these videos if you need even more help. This is all three of these tools are going to help you as you move to your homework and then eventually to your tests to be successful. If you have any questions or something doesn't make sense or it's not being clearly explained, feel free to reach out to your instructor. They would be more than happy to help you. So that being said, we're going to get into complex numbers. So to get started, again, we have scripture. Sometimes the scripture is going to apply really well. Sometimes it's going to feel like this is what we're learning about or this is encouragement for our learning. And sometimes it's just good wisdom to apply to our lives and to think about at the beginning of each day. So Romans 11:33 says, "Oh, the depth and the riches and the wisdom and the knowledge of God." It goes on to say how unsearchable are his judgments, and his paths are beyond tracing out or inscrutable. And so just this idea of this depth and rich and wisdom and knowledge and inscrutable paths are what seems to be invisible sometimes is made visible with a little bit of exploration, and that's kind of what we're going to do today. We are going to look at a rule from the 6th, maybe 7th grade that you may have heard, and flip it kind of on its head. Then we're going to take what was once invisible and make it visible. So you may have heard from the 6th grade that you cannot take the square root of a negative number, or the cube root, or the fourth root, or an even root of a negative number. Today we're going to define it. And we're going to say, when you do take the root of -1, we're defining that as I. Just a quick note that what this does, if we square both sides, because you're allowed to, what you do to one side, you have to do to the other, it leaves us with I squared on the right, and the square cancels out the square root, and we've got -1. That's going to come up and come into play a lot today as we work through this section. So let's jump right in to imaginary and complex numbers. Imaginary and complex numbers are made up of two parts. They have a real part, A, and an imaginary part, B. The imaginary part is the coefficient that's sitting in front of the I. So before we get started, we're going to do a little bit of review on just reducing radicals and applying this -1 square root inside of this radical. So if you remember, radicals can be reduced by breaking apart the inside into its factors. And so -24 can be broken apart as the square root of -1 times, and then we're going to think about the factors and say, are there any perfect square factors that we could use? So we're going to say 4 times 6, because 4 is a perfect square. And then what we can do, because square roots are properties of exponents, if you remember, x to the 1/2 is the exact same thing as the square root of x. So we can break this apart using the properties of exponents that distribute across multiplication to say this is the same thing as -1 times √4 times √6. And you'll see two of these we can reduce. From today, the -1 is defined as I, and I hope that you know the √4 already. And so we've got I times 2 times √6, and we'll rewrite that to put the I after the coefficient just to look like all the other variables we've ever worked with, and call that 2I √6. And there you go. It's a little bit of reducing radicals. This next try-it doesn't happen as much. We don't plot numbers on the complex numbers on the complex plane a whole lot, but it's good to see in future math classes this is going to come up, graphing complex numbers. So what we're going to do is we're just going to define the x and y axis as the real part and the imaginary part. And we're going to plot it like you would any point. And so we're going to have a real part of -4 and an imaginary part of, there's an invisible 1 right there, so -1. And we're going to plot the point -4, -1 on the graph and call that -4 minus I. You can see their example as well. teaching you how to plot points on the Cartesian grid. Except for this grid, we're kind of manipulating a little bit, so it's not the XY grid. It's the real part, imaginary part grid, where the real is the x-axis and imaginary is the y. Again, that might not be something that you'll see a whole lot, but it is not too hard and it's worth knowing. Subtracting these things and adding these is going to feel really similar to any work you did with variables already in the last section. So if we go to subtract two numbers, 3 minus 4i is a complex number on its own, and we're going to subtract 2 plus 5i from it, and we are going to treat the I exactly like a variable. The only thing that may come up at some point is that I squared term reducing. We won't see that this time, but let's keep going. So we're going to distribute that negative sign just like it's a negative 1, because technically there is a 1, an invisible 1 multiplied right there. So we distribute that negative 1, and we get 3 minus 4i minus 2 minus 5i. And if we combine like terms, the blue terms are like, the red terms are like, and we get 3 minus 2 is 1, and negative 4 and negative 5 is negative 9i. And you'll see that subtracting i's is very similar to subtracting any variable. I'm going to give you a little bit of time. It says also try adding them, so I'm going to give you a chance to try to add those numbers real quick. So if you want to take 5 seconds, you could pause the video. I'll give you 5 seconds. Try to add those two numbers that we already subtracted, and I'll give you the answer in about 5 seconds. All right, if you think you got it, maybe you got 5 plus I as your addition. If you did, congratulations, you can add complex numbers. All right, multiplication we're going to see is a little bit different. It still is going to be treated exactly like it's a constant. We just might see something cool happen sometimes. Or variable. We're going to treat the I like a variable, not a constant. So we're going to distribute that 1/2. We're going to get 5 over 2 minus 2 over 2i. And if you know 2 over 2 reduces 2, 5 over 2 minus just 1i hanging out by itself. Multiplication, we treat it just like we would treat a variable multiplication from the last section that we did. Now sometimes multiplication results in an interesting result. So right here, we're going to FOIL. If you remember first, outer, inner, last. So I'll go ahead and do that in color so you can see where each thing happens. So 3 times 2 is 6. That's the first term of each binomial. The outside terms would be 3 times 3 is positive 9i. The inside terms, negative 4i times 2 is negative 8i. And the last terms, negative 4 times 3 is negative 12. But here's where the interesting thing happens. I times I is I squared. And if you remember from earlier, we had a term or definition or a result from squaring both sides of that definition where we get to say, hey, that I squared we've seen before. I squared is technically negative 1. And so we can reduce this entire equation by saying 6. We're going to combine these two like terms plus I minus 12 times negative 1. And negative 12 times negative 1 is a positive 12. So 6 plus I plus 12. And that gives us 18 plus I. This is a good thing to note here because we've already done a few examples. Notice as we write our answer, we've been writing it in 2 parts, a real part and an imaginary part. It's important as you report your answer to do that. Your homework is going to really prompt you to do that. On your homework, it's going to even give you 2 different bubbles for the real part and the imaginary part to fill in. But you can see if we scroll up through all the answers, we've had a real part, which is the real number, and an imaginary part, which has an I attached to it. So all of these answers so far have been split up into 2. All right. All right, we're getting close to the end here. We're going to have one easy topic and then what I think is the hardest type of problem of this entire section. But first, we're going to have the easiest one. This idea of a complex conjugate is found by changing the sign of the imaginary part. So all we're going to do is change the sign associated with I. Sometimes you'll see this written as x bar with a bar over it. Sometimes you'll see it written as xc, like the conjugate. So let's go ahead, and I'm going to define this term as x, so I can give you a x bar as your conjugate. And all we're going to do is take that middle term, the sign associated with the I, and change it. So now it's a subtraction sign instead of an addition sign. And that is your complex conjugate. Why we're doing this is going to come into view in the next problem. But to find the complex conjugate is not the most difficult problem of this section. Now, why we're doing that comes into play when we divide two complex numbers. And so we're going to divide 2 plus 5i by 4 minus I. And we can read these steps up above if you want to pause the video and read these steps, or read through your textbook, or if you've read it before, that's great. But I'll walk you through the steps here using the complex conjugate to divide two complex numbers. All right, so the first thing we're going to do is we're going to multiply by the complex conjugate on the bottom. But you may be asking yourself, are you allowed to do that? Can you just multiply by a complex conjugate whenever you want to? You can't, but you are allowed to multiply by 1 in a really cool way. And so all we've done here is, maybe I'll do this in a different color. All we've done here is multiply by 1 in a really interesting way that's going to help us simplify our result a lot. And so I might do this a little faster than the last one. If you need practice foiling, pause the video, practice your FOIL, but I'll work through it a little bit faster so you can save some time. 4 times 4 on the bottom is 16. 4 times I is positive 4i. Negative I times 4 is negative 4i. You might see something interesting there in the middle. And I times I is negative I squared. We're going to have to do the same thing on the top. So what did we do to both? We FOILed the top and the bottom. And so we're going to do the same thing where we get 8, positive 2i, positive 20i, extend that a little bit, and plus 5i squared. And you may have already thought to yourself, hey, I see I squareds, those are going to reduce, and I see some like terms that are going to simplify. And that's true. So we see this positive 4i and negative 4i cancel out. We also see this I squared, if you said it earlier. Oh, I squared, isn't that the same thing as negative 1? It is. So on the bottom, all we have is 16 minus a negative 1. Because the minus sign from the subtraction still stays. And then we introduce the parenthesis negative 1 from the I squared. And on the top, we have some similar like terms combining. We have 8 plus 22i plus 5. Here's that I squared happening again, times negative 1. And so the bottom's a little bit easier to do, and the result of the complex conjugate, that is so interesting. 16 minus negative 1 is 17. No, yes, 17. There's the result of the complex conjugate. When we multiply by that interesting conjugate, we get a whole number on the bottom. This is the reason we multiply by a conjugate over conjugate. So the bottom reduces to a whole number, and we can split our result into the real and imaginary part. Then on the top, you get 8 plus, well, I can go ahead and do that. 8 plus a negative 5 is 3 plus 22i. And then as a last step, just like all the other solutions, we're going to split up the real part and the imaginary part using a common denominator and the properties of fractions and get a result of 3 over 17 as the real part and 22 over 17 as the imaginary part. Real, imaginary part. All right, we're going to finish up this section with just looking at something cool about I, a cool thing that happens when you work with these I terms. Here, I can zoom out so you can get a whole pause on that if you need to. If you need to practice foiling, practice reducing, practice combining like terms, there's a solution for you. All right, we're going to look at these I terms and how the powers of I are cyclical. I to the first power is just I, and if you remember the definition of this, it was the root of -1. Now, using properties of exponents, that exponents can be split up, we're going to say I squared is just the same thing as I times I. And we already said this today. This just results in -1 when you cancel the square root. Now, I to the third power is where this starts getting interesting. We're going to call this I squared times I, and we just defined I squared as -1, and so we get -1 rooted. And the fourth power is where it gets cool. You can break up I4, or I to the fourth power, into I squared times I squared, because you would add those exponents and turn back into 4 if you wanted to recombine it. And I squared we just defined as -1 for both of them, and so I to the fourth power is just 1, which means all of the next 4 terms are going to be some factorization where I4 happens. And so I5 is just I4 times I, which would just be 1 times I, which just gives us I as a final answer. So I to the fifth power is exactly the same as I, and that's why we call it cyclical or cyclic, because it's going to repeat every 4 terms. It repeats the pattern. I4, or I to the fourth power, is the same thing as I to the sixth is I to the fourth times I squared, which would be 1 times I squared, which is -1, and it repeats again. I to the seventh, we would multiply by I3, and this is just -1. And I8th is I4 times I to the fourth power, which would just give us 1 times 1, which is just 1. And so you can see all of these terms repeat. If you add 4 to the exponent, the terms repeat and repeat and repeat. And we would see that pattern happen again for any number. So note, if n is any integer, and you take a divisible number by 4 and add 1, you're going to result back in I. If you add 2, you're going to result back in -1. If you add 3, you're going to result back in -I, which is the same thing as -1. That's kind of the one that is a little weirder. And if the power is divisible by 4, you just get 1. And so how does this work out, or how can you use this to your advantage? You can take I18 and say, well, this is the same thing, and I'll make it as I4 times I4, that would be I8, times I4, that would be I12, times I4, that would be I16, because 4 times is 16. So what's left over? This is where the cyclical power happens, I squared. And add those exponents to make sure I did my math right. 4 plus 4 plus 4 plus 4 is 16, plus 2 is 18. And so this, if we keep the colors consistent, is 1 times 1 times 1 times 1 times whatever I squared was from the beginning of the day, which was -1. And so our full answer is just -1. I to the 18th power is -1, just like I squared is -1. And that is section 2.4. That is complex numbers. I would encourage you to go and look through the blank notes and the completed notes again, review this material and make sure you're ready for it, because a few of these questions will show up on each test, on the test for chapter 2, but also the final exam. And so mastering these concepts is really important. Again, if you have any questions, reach out to your instructor. I wish you the best. I hope you're happy studying in college algebra, and I'll see you next time. Thank you.